Chapter 6 is about set theory. Before we get into Chapter 6, however, let's go back to Section 1-2 at the beginning, where we have the basic introduction of the notation dealing with sets and some very basic concepts. First of all, a set is nothing more than a collection of elements. An important item here is that the order does not matter. Several ways are around for being able to describe what is in a set. One is to do a set roster, where we simply list the elements in the set, and we use curly braces here to distinguish where the set is. In some ways, the curly braces are kind of like a box, and the things that are in the box are the elements of the set, and here we're saying set A is equal to this. A second way that we could talk about the set is to use set builder notation. Here I've said set A is the set of all the x's that are integers, where x is between 1 and 3, inclusive of 1 and 3. Notice, set A is the same set in both of these. We've just distinguished it different ways. Some other notation dealing with this. We can say 1 is an element of the set 1, 2, 3 because it is one of the elements in there. However, you have to be careful. The set containing 1 is not an element of that, and we show it's not an element this way. All right. On the other hand, the set containing 1 is an element of this set. Here we have a set that contains another set. One of those elements is indeed another set. Is the set containing 1 then equal to 1? No, they are different things. Let's make sure you're really comfortable with some of this notation. How many elements are in this set? Well, when you first look at it, you can see the set contains 2, 2, 2, and 2. But those are really all the same element. So there's only one element in that set, but we've managed to list it 4 times. This is a roster, just like a class roster. And if your name appeared on the roster twice, you'd still only be in the class once. Another word for the number of elements in a set, we'll learn later on, is its cardinality. So we'd say the cardinality of this set is 1. How many elements are in this set? This is a set that has 2 elements. The 2 elements are 0 and the set containing 0. The set containing 0 and 0 are different elements. Is the set containing 0 an element of this set? Yes, because the set containing 0 is one of the elements here. Is the set containing 0 an element of the set containing 0? No, because this set doesn't contain a set containing 0. Is 0 an element of the set that contains these 2 sets? No, it is not. This notation is something you should become comfortable with, and you should try the problems in Section 1-2 to make sure you're comfortable with this. Another important idea that's been introduced in Section 1-2 is the idea of a subset. We use this notation. A is a subset of B, means, in other words, if and only if here, for every x that's an element of the first set, x is an element of the second set. They also describe in your text what is a proper subset. And I'm using this little different symbol for proper subset, which your text doesn't use, but it's a very common symbol. See this symbol up here saying it's a subset, sort of says everything that is in A is contained in B. This says everything that is in A is contained in B, meaning A is a subset of B, and there's something in B that is not in A. When we say A is a subset of B, if I were going to be drawing diagrams of these, this one is usually the bullseye diagram, where everything that is in A is inside of B. But you could have A and B being the same collection, in which case that is also going to be a subset, but it is not a proper subset. To be a proper subset, there has to be something that is in B that's not in A. We're going to say two sets are equal, it's all in the same box, if you will, if and only if A is a subset of B and B is a subset of A. Sometimes we will do notation like this. To say A is not a subset of B, that could mean perhaps that there's an overlap between A and B, but there's some things that are in A and not in B. But it could also mean the sets look like this, which we'll discover when we get involved with Chapter 6, is saying it's a disjoint set. Another term that's introduced in section 1.2 is the idea of an ordered pair. Ordered pairs are items where the order does matter. When we use the curly braces that we had dealing with sets, these things, sets the order did not matter, here the order does matter. And we can say that this ordered pair AB is the same as the ordered pair CD if A is the same as C and B is the same as D. You're probably used to seeing ordered pairs in places like Cartesian coordinate systems, where you take two number lines and make them at a right angle, and you make an ordered pair where the first item is the x variable and the second item is the y variable. So here you can see that the ordered pair 1, 2 is not the same thing as the ordered pair 2, 1, because 1, 2 has an x value of 1 and a y value of 2, and 2, 1 is just the reverse, an x value of 2 and a y value of 1. This is very different from seeing that with the curly braces, those two sets, which each have two elements, are the same set, and so they are equal. Associated with these ordered pairs are Cartesian products. Cartesian products are what we were getting here when we were taking the two number lines and crossing them with each other and looking at the ordered pairs. A Cartesian product, which by the way is named after René Descartes, the famous French philosopher and mathematician. The Cartesian products are made when you look at a set A cross set B by looking at all the ordered pairs where we take one element from set A and one element from set B. If I have the two sets A and B, where A is 1 and 2 and B is 3 and 4, I should be more precise in my language, the set A is the set containing the elements 1 and 2, and the set B is the set containing the elements 3 and 4. A cross B is going to be another set that's going to be a collection of ordered pairs. It's going to have the 1 paired with the 3, the 1 paired with the 4, the 2 paired with the 3, and the 2 paired with the 4. When the cardinality here is 2 and the cardinality here is 2, here we get a collection in A cross B with a set that has a cardinality of 4. So the cardinality times the cardinality shows us the cardinality. Notice we could just as easily do A cross A, and we could get the ordered pairs 1, 1, 1, 2, 2, 1, and 2, 2. And again, the rule about cardinality holds as before. One of the things you should do is you should take a look at the problems that are in the You Should Be Able to Do Problems Like section for set 1, 2, and make sure you understand the notation for these. And if you have any questions, let me know, because we're going to need to know this kind of notation in doing Chapter 6.